So, as I said, today we are going to graph lots of rational functions. So, what rational function is? The definition. The rational function is a function with a variable in the denominator. So, function with the variable in the denominator. It's a function with a variable in the denominator. The graph of such function is called a hyperbola. And now we'll see how it looks. Hyperbola. So the simplest rational function, right? We want the variable in the denominator, everything else the simplest, as simple as possible. So y equal 1 over x. Thinking 2 classes ago or 3 classes ago, what is the restriction for the domain of this function? Denominator cannot be 0, right? So if I figure out the domain of this function, what I need to do is figure out the restriction on the domain. X should not be 0. That's my restriction on the domain. So how can I write that domain? Domain is, in set builder notation, it would be something like x such, all the x such as x is not equal to 0. You could also use the interval notation, and then you would say from negative infinity to 0, union 0 to positive infinity.
Wait,
So,
why?
because we cannot divide by 0, right? If I choose x equals 0 and try to figure out what my value for y is, I would have to calculate 1 divided by 0, and that's undefined.
Okay.
Okay. So the domain is simple. If I have chosen 0 as my value for x, I'll get error. Let's see what happens if I choose values on the both sides of 0. So getting very close to 0, but not quite reaching it. So I will look at the values negative 1 over 4, negative 1 over 2, negative 1 and 2. And then same on the other side. So positive 1 over 4, positive 1 over 2, 1, 2, I could do 4.
Why did you get those numbers?
I'm just choosing any numbers, right? Because when we plot the function, we could choose any numbers for x, calculate the values for y, plot the points, and connect them to get the graph. Basic, no calculators used, right? That's how we did it before we started using calculators.
Wait, but why wouldn't you just use whole numbers?
Well, because I want to see what happens as I get very close to 0, to my restricted value. That's why I'm choosing those fractions here. I want to see what will happen.
Shouldn't that 2 below the x, shouldn't that be a negative?
Oh, here, yes. That's negative. That's right. Okay, so now plugging in my x values into the formula to figure out corresponding y. 1 divided by negative 2 is negative 1 over 2. 1 divided by negative 1 is negative 1. 1 divided by negative 1 over 2 is negative 2. Correct? 1 divided by negative 1 over 4 is negative 4. Everybody with me? Skipping 0 because I know I cannot divide by 0. That's an error. 1 divided by 1 over 4 is what?
4?
4. 1 divided by 1 over 2 is
2.
2. 1 divided by 1 is
1.
1. And then 1 divided by 2 is
1/2.
half. And then 1 divided by 4 is
1.
1. So now I have few points from my graph that I could plot. Okay, let's see. Negative 2, negative 1 over 2. My graph will not be pretty because the, not perfect calibration. So negative 2, negative 1 over 2. About here. See, it's not, sorry, not perfect. Negative 1, negative 1. About here. Should I try again? Yes.
Still don't get where you concluded that 0 should be like a point in the domain. did you just choose 0 and just go from there?
No.
Is there a particular reason why you chose there?
Because you have denominator, and I cannot choose such values of x that will set my denominator to 0.
So why you choose 0? You can't do it on
Because if you take your calculator and try to
I
calculate,
know 1 divided by 0.
yes.
But why do you put the 0 there? Like,
Oh, right here.
yeah.
Oh, I know that this is, I have to skip it, right? This value I cannot choose for x, but I want to see what happens before it and after it. Yeah, that's why I put it in the middle. Okay, so again, I'll try to plot it a bit better. Okay, plotting the point -2, -12. So about here, oh better. -1, -1. Go ahead, -1/2, -2. And then this one will be very hard to plot for me. -1/4, -4. So you're closer to 0 on x, but and then right here, very close to x-axis. I mean y-axis, but not quite reaching it. Then 1/4 for here. 1/2 2.
Wait,
Here.
wait. I'm confused.
So I skip 0 and then I go to 1/4 and 4. So I'm right there.
Wait, how did you do?
Hmm?
Never mind.
Just plotting my points, nothing else. 1, 1, 2/2, and then 4, 1/4. So now if I connect my points, right, and I'm mindful about what will happen as I change my x, take smaller x, right, go to the left. And what happens to my y if I get closer to 0 for x? This is what I will get.
And you want us to put arrows on the end?
Yes, this is just to indicate that we're not done. This is not where the graph starts and ends. We can continue going all the way to the left, all the way to the right, and as close to 0 as we can, right? As we want, not as we can. Yes?
How did you get the y value?
Oh, I plugged in x into the formula. Right? So for every x that I chose, I plug it into the formula to calculate my y value. Right? That's how the graph functions. Okay, so just by looking at these, yes.
I just have a quick question. So for for the basic hyperbola, y equals 1/x, that's like the basic hyperbola function. So in that situation, the domain is like what's down there, negative infinity to 0, and then 0 to infinity. That's like the basic. Okay.
Hyperbola. Yep. And we figured that out by looking at the equation, right? Okay, so just think about it. If I choose my x, like x equals 1000, right? My y will be 1/1000. So it will get even closer to my x-axis. But will I ever reach the x-axis? No, right? Because my function, if you look at this, my fraction is 1/something. And if my numerator is not 0, then my fraction will never be 0. So I'll get very, very close to the x-axis, but I will never reach it. Right? So now thinking about this, what do you think my range is? The range? Yes.
Negative infinity to positive infinity
Except the value what?
of 0.
0, right? So it's all the y's such that y are not 0, because we will never reach that point where the y will be 0.
So basically, it's the same as x. You're just
Well, no, I don't like that rule.
so it's no, and this is
Yes.
what I was asking for. So it's negative for y.
So now let's talk about the right-hand behavior and left-hand behavior. As we said, as I increase x to 1000, 10,000, whatever, what do you think will happen with y? So if x goes to infinity, where does y go? No, right here, right? I increase x, y gets closer to what value?
Positive infinity. No, it's regular infinity.
So you see, I'm increasing my x, 1, 2, 4, my y becomes 1, 1 over 2, 1 over 4. As x goes to 1000, y will be 1 over 1000. As I increase x more, y is 1 over x, so it gets closer and closer to 0. Right? It will never reach it, but the right end behavior is 0. Y gets closer and closer to 0. Do you see that? And then on the left side, as x gets closer and closer to negative infinity, y gets closer and closer to 0 again. Just from the other side. It's still negative, but it's closer and closer to 0. Okay, questions about this? No. So the interesting thing about this graph, this kind of graph, is that because we have this restriction in our domain, we can never cross this line, right? So we cannot have x equals 0, so it means that our graph can never cross the line x equals 0, right? And as the result, because we can get very close to it, to this line, so as the result, our graph is kind of like climbs up and down along the line. Never reaching it, never crossing it, but it gets very, very close to it. And for the horizontal line here, once again, our graph is kind of crawling along the line, along the x-axis, but it never reaches it, never crosses it, right? So that's the thing about the hyperbolas, that's their like real property or most interesting property. And we call those lines asymptote. So the asymptote is the line that the graph gets very close to, but doesn't cross. Gets close to, but doesn't cross. So asymptote is a line that the graph gets very close to, but does not cross. And the rational functions have two types of asymptotes, as we saw. The vertical asymptote that is written as x equals something, and the horizontal asymptote that is written as y equals something. Two types of asymptotes. So I think in the previous classes you used this absurd word, either books hoi or hoi books, whatever you've learned, right? That's to help you remember the equation for vertical versus horizontal lines. So V stands for vertical, U stands for undefined slope, and then x equals is the formula. And then the hoi is what? Horizontal line, zero slope, and phi equals is your formula. Very good. Okay, so let's look at another simple example. It's almost the same as the first one, just a little bit different denominator. So something will change. So what do you think will change?
The x.
So
the domain.
Domain, right? The denominator is different, so the restriction in our domain will be a little bit different, correct? So what is going to be my domain? I don't want my denominator to be 0. Domain restriction. So if I solve for the bad x, it's minus 1 minus 1, it's x equals negative 1. That's the x value I do not want. So my domain in interval notation will be what? Negative infinity to 1. Oh, to negative 1, sorry. Negative infinity to negative 1 with parentheses, union negative 1 to positive infinity. Yes?
On the domain restriction, should that equal some
That's why I put restriction.
Oh.
So like to not get confused. But yes.
So when you're trying to
As we figured out the domain restriction, can we now think about what happens in terms of the vertical asymptote? What do you think the vertical asymptote will be? I cannot have -1, but I can get as close to it as I want, right? So I know that my function would probably climb up and down the line x equals -1, correct? Because I can get very close to that -1 value, but I can never choose it. So it's, if you remember about our previous example, that was my restriction on the domain, so I could get very close but not quite reach that value, right? So my function climbed up and down that line, that vertical asymptote. So what do you think our vertical asymptote is? Should probably be x equals -1. Is this intuitive? More or less? How I got to it? Good. You have to give me some kind of signal. Okay. So when we figure out the asymptotes, it's a good idea to graph them with the dotted line, just to remind yourself that we don't want to cross it ever with our graph. Okay, so the range here will have like specific rules to follow, but just intuitively, what the value of y do you think we can never get? Whatever x I choose, I cannot out of this function. What do you think the value for y that I will never get out?
-1.
Well, I can get -1. But my numerator of the fraction is 1. Whatever I divide it by, I will never get what? 0. Somebody said 0. I'll just go with it. Yes? Because if numerator is positive number, whatever I put in denominator, I will get some number. I can never get 0. Correct? So the range, no, it's going right. The range, time for lunch. Oh, come on, let's just write down the range.
No.
So the range will be -infinity 0, union 0 to positive infinity. Because I can never get 0. Just intuitively, we are just playing with it. So it means, wait, give me 1 minute. It means that the horizontal asymptote will probably be that 0, right? Same, x-intercept. Because I will never cross that line, because I can never have a point on my graph with the value of y 0.
So y equals what?
So y equals 0 is my asymptote. Okay, that's right. Okay, so we kind of intuitively figured out our horizontal and vertical asymptotes for this particular function, right? So it was like a stretch, intuitively. We figured that's how it goes. Oh, I want to also show you another way, and maybe, so if we want to graph this function, right, we could just, again, find points on both sides of our restricted value in the domain. So I'll just choose a couple of points on both sides. -1, the next good point is, I want the fractions because I want to see what's happening over there. So I'll put -1 over 2 here, and then maybe 0, and maybe 1 over 2. And I can put like 4 also, just since I have space. And then on the other side of -1, I'll put -3 over 4, over 2, 3 over 2, and then -2. Just getting farther and farther away from my restricted value.
Why wouldn't you have just the same numbers that are?
I could, no, because they cannot be the same,
Not
right?
the same, but I'm saying like why wouldn't you put 1?
1/2 is on which side? 1/2 is not, both 1/2 positive and negatives are on the right of my restricted value, of my asymptote.
Oh,
So I have to go away
I see.
from both sides.
I was confused.
Wait, I have a question.
Yes.
I went ahead and already did my numbers and my dots. Is it okay if I did that, or would you like me to change that?
No, you can use whatever numbers as long as you have them on both sides of the asymptote. So just plugging in my x's to figure out corresponding y. 1 over -2 plus 1 is -1. 1 over -3 over 2 plus 1 is -2. 1 over negative 1 over 2 plus 1 is 2. You can check me with the calculator. 0 gives me 1. All I'm doing is plugging in my x's into the formula. 1 over 2 plus 1 is, what is it? 2 over 3. And,
I understand how you got to the
4 and x gives me 1 over 4 plus 1 of 1 over 5. If I plot these points on my graph, let's see what happens. Negative 2, negative 1, right here. Negative 3 over 2 becomes negative 2. Right? If I have another negative 4 here, that will give me negative 4 plus 1 is negative 3, negative 1 over 3, negative 1 over 3. So I get closer and closer to my asymptote, you see? Like this, on this side. And on the other side, I have negative 1 over 2, 2. So here, 0, 1, another point. 1 over 2, 2 over 3. So somewhere here. And then I chose 4, 1 over 5. Just to show that I'm getting closer and closer to my horizontal asymptote. When I connect these points, I'll get something like this. So again, hyperbola, very similar shape as the very first example that we had. But the asymptotes moved. Horizontal asymptote is still y equals 0, but the vertical asymptote moved 1 to the left. Questions? No. And don't worry, you will not have to do all this analysis in your head every single time you work on the problem. So this third example is on not the second page, but the third page. Here we just want you to be able to recognize some of these properties just by looking at the graph, because normally what you would do, you would plug in the function into calculator, get the graph out, right? And then from the graph, how can we recognize all these properties? That's what we want to see here. So the new function here, y equals x over x plus 2, now I have variable in numerator and denominator. So something a little bit more complicated, a little bit different. And let's say we already plugged this into calculator, and this is the graph that we got. So just by looking at this graph, what do you think my vertical asymptote here is? Vertical asymptote.
Negative.
The line that the graph hugs but never crosses.
-2.
X equals negative 2. Oh, vertical. X equals negative 2. So if I draw it here, it will go through x equals
see
negative.
that it's kind of like
Yep.
finding the negative.
Exactly. Yes. And of course, because we kind of climb up and down this line, it tells us that we will never really reach this line. So the domain will not include what value of x? Negative 2. So my domain will be all values of x such that x not equal to negative 2. That's in the set builder notation. I can also use the interval notation to represent it, but for now I won't. Okay, so what about my horizontal asymptote? Do we see the horizontal asymptote? The horizontal line that my graph is having,
1.
yes. 1. So y equals 1 right here. If I draw it, looks like we are hugging this line, x equals 1. And so that tells me that the range, right, if my graph never crosses that, what is the value in the range that is not included?
Oh, I'm sorry, that's
Oh, you're asking question.
So are both of them x?
Oh, I'm sorry, y, yes, y, it's y. Horizontal y, right? Thank you. Horizontal is y equals 1. Sorry about that. Right? This is the line. Y equals. Horizontal. Y equals.
So if you didn't have it already graphed.
Okay, so if the horizontal asymptote is y equals 1, then what does it mean for my range? What value is not included in the range, for example? You. What value will not be included in the range? 1. So range would include everything from negative infinity to 1 and from 1 to infinity, but will not include 1. But we will get very close to 1, but we will never have that point on the graph that will have y value 1. Good. And just from looking at the graph, what are the zeros? What are the
0,
0, 0, right? The x-intercept or 0 is 0, 0. What about y-intercept?
0, 0.
The 0, 0, very good. What if I didn't have the graph? How would I figure out my zeros? What do I need to do if I only have equation? How do I find zeros? Or if I don't want to graph it? Just by looking at the equation, how do I figure out zeros? Plug what in? For x-intercept, which coordinate do I know, x or y? For every x-intercept, what value do I know? Every x-intercept always have 0 as what? Y or x? Y, right? So I know for x-intercept, y has to be 0. So if I take the equation for y and set it to 0 and solve it, right, I will get my 0, my x-intercept. When I have the fraction like this, here I have a fraction x divided by x plus 2 equals 0. Which should equal to 0, numerator or denominator, so that I get 0? I have a fraction. Which number, numerator or denominator, has to be 0 so that the whole fraction is 0? Numerator. So to find my x-intercept, I will have to set numerator to 0, solve for x, find my zeros, right? For the y-intercept though, for y-intercept, which coordinate do I know? X or y? X. So x equals 0 for every single y-intercept, for every single function. Oops. So all I need to do is plug in 0 into my formula. 0 over 0 plus 2 equals 0. And this is the y-coordinate of my y-intercept, right? I don't even need the graph to figure out those two. Okay, so, yes?
Could you write in set over to range?
I could. I could. Okay, so now as x goes all the way to infinity, my right-hand behavior, I go all the way to the right. What happens to my y? Gets closer and closer to what?
0.
0. Very good. No, not 0. Come on. No.
Only 1.
1. Right? Our horizontal asymptote, 1. Oh, almost 100%. And then as we go all the way to the left, 1. Y gets closer and closer to 1. So you see how horizontal asymptote is related to the end behaviors, right?
Is that
And
every
vertical asymptote is related to domain. Yes?
Is that every case relation?
Yeah. Okay, any questions here? Finally, let's go to our graphic organizer. I put everything here on one page, and I should not have, because there's now not enough space. We'll try. Okay, so I'll just make it large. Okay, so we'll fill it in like clockwise or counterclockwise. I want to see my key, so I know exactly what to write, so it's not missing. Okay, so if I have the rational function, this is not the most generic case, by the way. I can have any kind of polynomial in numerator or denominator, but we'll just do the simple one here. So once again, how do we figure out the vertical asymptote? Think about our examples. Vertical asymptote related to what? Domain or range? Vertical.
Domain.
Domain, right? So how to find vertical asymptote? We need to set our denominator to 0 to find that restricted value. So remember, folks, set denominator to 0, solve for x. and then we write it as x equals whatever we got. So set denominator to 0, get that restricted domain value, use it for your equation x equals. Good. So from here, the logical step, domain, right? Domain and vertical asymptotes are very much related, so how to find the domain? All values included except our vertical asymptote value. I'll use V8 for not for Virginia, but for vertical asymptotes. And then we can use either set builder, all x such that x not equal to our VA vertical asymptote, or you could use interval notation from negative infinity to my VA value, union VA value to infinity. Parentheses so that we don't include that restricted value. Okay? Now, let's go to horizontal asymptote. Again, remember, horizontal asymptote was related to the end behaviors and to range, right? So this is the rule that we're going to use, and I can explain it using that same idea that's right there, or you can derive it for yourself if you're interested to, but it's out of scope for this class. So how to find it? Compare the degree of the polynomials in numerator and denominator. So degree over degree. So compare what kind of polynomial you have in numerator and denominator. If the degree is exactly the same, so same. If same degree, same, then your horizontal asymptote would depend on the leading coefficients A and C. So then it's A divided by C. Okay, that's your horizontal asymptote. Y equal A divided by C, that's your value, yes.
So what do you mean by
If they are the same, then we just look at the ratio between the leading coefficients. Leading coefficient A, leading coefficient C. That gives you the number to use for horizontal asymptote. If the degree of the polynomial in numerator is less and the degree of the polynomial on the bottom is greater, then you use 0. Y equals 0 is your horizontal asymptote. Just as we had in those two first examples, 1 over x plus 1, the horizontal asymptote was y equals 0. So this gives you. And the third case, obviously, is when the polynomial on the top has greater degree than the one on the bottom. We will not have those in our class. This is out of scope for us, but those would not have any horizontal asymptote. They will have different, like, what is it called? Slant asymptotes, but not horizontal. So out of scope, if you want to make that count. Okay, so done with horizontal asymptote. Obviously, if I know the horizontal asymptote, I can figure out the range, right? Because we never cross the horizontal asymptote. It means that my function will, the range of the function will not include this value, right? That's what we did here. Remember?
So all values except for the horizontal.
Yes, exactly. So how to find it? All values except horizontal asymptote. And then again, we can use either set builder or what is it? Interval notation. So negative infinity to horizontal asymptote is parenthesis. Union horizontal asymptote, all these parentheses because we don't want to include it. Okay. because our graph will never cross that line. So it means that there is no point on the graph that has that particular y coordinate. And behaviors. Again, very related to my range into my horizontal, well, not the range, but horizontal asymptote. Right? As my x increases all the way to positive infinity, or as my x decreases all the way to negative infinity, I'm still hugging that horizontal asymptote. So for the right and left end behaviors, I need to use the horizontal asymptote number. Before we had those arms going up or down, so our end behaviors were either positive or negative infinity. Now it's just the number different. Good? Now going to the right. Y-intercept and x-intercept, nothing changes. Just as before, what we need to do for y-intercept, it's where my graph crosses y-axis. So what I need to do is plug 0 for x. And so I write 0, comma, whatever I got there. Here, if you just look at this formula, it would be b over d, correct? Because if x is 0, a times 0 is 0, and c times 0 is 0, so all I have left is b over d. Right? So here, it's really like this, b over d. Okay, so zeros, again, this is just as before, as we normally do. How do we find 0? It's where my graph crosses what axis?
X.
Where graph crosses x-axis, right? So I can set numerator to 0, and solve for x. Because remember, if I have a fraction and I want it to equal 0, I need numerator to be 0. I don't even worry about the denominator anymore. And we write it as substance 0.
So you don't
Oh,
think
because it's not O, it's number 0 usually. Sorry, it's confusing.
That messed me up earlier. It's like, wait a minute.
Oh, you think it's not 0 or something?
That makes sense.
Sorry about 0. Don't put that line. So let's just write these notes. These tips on how to graph rational functions manually, by hand. By hand. So first step, we find the horizontal and vertical asymptotes. So VA and HA. Find the vertical and horizontal asymptotes. The second step is find one point on each side of the vertical asymptote. The vertical. And plot them. Just one point on each side. And then sketch the graph, remembering the basic, the basic shape. And you remember the graph never cross the asymptote. So figure out what the asymptotes are. Graph them with dotted lines. Plot one point on each side of the vertical asymptote to know where you are, and then sketch the graph. Just remember the basic shape and remember that we never cross asymptotes. Okay, so let's try. Finally, example. I have the function here y equals 4 over x minus 2. Let's use our graphic organizer to figure out all the properties. No need to do any kind of analysis here or guesses. Horizontal asymptote. How do we find horizontal asymptote? We look at our rules. We compare the degrees, right? First, we compare the degrees of the polynomials in numerator denominator. What we have is 0 over 1. I'm not going to put it here. But for horizontal asymptote, degrees are...
Oh, because it's the highest degree.
Yes, so degree over degree is 0 over 1. I have 0 degree polynomial on the top, 1 degree polynomial on the bottom. The smaller degree on top means that my horizontal asset is what? Y equals what? Look at your organizer. What is it? 0.
So whatever the smaller one's on top, then what is that?
We don't have that in this class, I said. If this greater one on top, we will not have it. There is no horizontal asymptote.
Oh, but if the smaller one is on the top, then that means
Yes.
that whatever it is that number.
I don't know what you just said, sorry. Next, from horizontal asymptote, I can easily find the range, right? So what is the range? Look at the graphic organizer. The range, all values except horizontal asymptote value. So what I could put is all y's such that y not equal what? 0. Just going back to my organizer, using the rules. Also here, depends on horizontal asymptote, is what? End behaviors. Right? I can use my horizontal asymptote value to figure out my end behaviors. They both will have the same value, which is what? 0 and 0. Okay? Vertical asymptote. What do I do to find vertical asymptote? I
You said x minus 2 equals 0.
set denominator to 0. So vertical asymptote, I set my denominator x minus 2 to 0, solve for x. Plus 2, x equals 2. That's my vertical asymptote. X equals 2.
But if I have a vertical asymptote, it's a non-linear.
Yes. Go back to your graphic organizer. Make sure you know how to use it. So you don't ask these questions. From vertical asymptote, I can go to domain, right? That's where I use that number. What is my domain? We wrote all values except VA, which means all x values except x not equal to 2. Now zeros and y-intercept. Well, y-intercept is always super easy, right? Because all I need to do is use x equals 0, plug it into the formula. So 4 y-intercept, 4 divided by 0 minus 2 equals what? Negative 2. So negative 2 is my 0, negative 2 is my y-intercept. Finally, my zeros or x-intercepts. I'll just do it algebraically just because. What do I do to find it algebraically? Zeros, set numerator to 0. So I need to set numerator, which is just 4 equals 0. Is this ever true?
No.
No. So I don't have it. None. No zeros. None. And by the way, as we've seen from our examples before, whenever horizontal asymptote is y equals 0, it means that we can never cross x-axis, right? So by definition, I didn't even need to think twice. If horizontal asymptote is my x-axis, it means I will never cross it. So there is no 0, there is no x-intercept. I know it's a lot to put together, but just like when you work on your homework, try to connect all this in your head. Because it's all connected. It's like it all makes sense. Everything is related. But it's a lot. Okay, so we figured out all these properties based on this graphic organizer. Specific rules to use. Okay? Now, any questions about this?
We have nap time.
Huh?
We have nap time.
Nap time? I wish. I would totally join you, but... Okay, so now let's use these steps to graph the function manually. What we need to do, we found the vertical and horizontal asymptotes, y equals 0 and x equals 2. So let's plot them with the dotted line. Y equals 0 is just x-intercept. That's one of my asymptotes. The vertical asymptote is x equals 2. So it's vertical line that goes through x equals 2. I have two asymptotes on my graph. I know I will never cross them, but I need to figure, so I know there should be like, my graph will have these asymptotes. But where? That's the question. So all I need is find 2 points on both sides of the vertical asymptote. So what I'll use is my xy table. On the left of the vertical asymptote, I'll just use 0. X equals 0. If I plug this in, 4 over 0 minus 2 gives me negative 2. And now I choose the x on the other side of my vertical asymptote. Let's say 4. I can choose anything, right? But on the other side of the asymptote. So 4 divided by 4 minus 2 is what?
2.
2. If I plug in 4 here, 4 minus 2 is 2, 4 divided by 2 is 2. So here are the 2 points that I'll put. 0, negative 2 is 1. Right here, I'll use different color for it, actually. So the asymptotes are different color from the graph. So 0, negative 2, 0, negative 2, here is 1 point. And then 4, 2, 4, 2 is the other. And now, of course, this is just like, this is not precise, so of course it's not accurate, but I know where it is at least. My graph is in this corner and that corner. And sometimes you'll find cases when your graph is in these corners, the opposite corners. So that's why we want to plot those points to figure out where the graph is. Yes. Hannah, just so using calculator, as before, as always, we go to our y equals, we plug in whatever function we are working with. The only thing is, don't forget to put your denominator and your numerator in parentheses. That is super important, otherwise you will get wrong number. Well, when it's just 4, then you don't, whatever. 4 divided by, and then I put denominator into parentheses, x minus 2.
Are we still on the problem?
Yeah, same problem. Yeah, same problem. So 4 divided by x by parentheses, x minus 2 in parentheses. Now I graphed it. And this is what I get. So some calculators will show graph like this. Other calculators will actually show the line, which is the asymptote, vertical asymptote. But you have to make sure you don't include it as part of your graph. In your graph, if you include the asymptote, it should be dotted, so we know that your graph and asymptote, that is not the line. So here, you know, from this graph, I could easily see, well, kind of easily see that my horizontal asymptote is the x-axis, right? It's quite obvious. And for the vertical asymptote, well, this one is very nice, so unless, well, I recommend always doing the vertical asymptote algebraically. Just because sometimes, what if it's like 2 and 1/10, right? Something weird, a little decimal, yeah, just over. So it's very hard to see from here. But in general, the calculator obviously gives you the shape of the graph, and then you can go to table, make sure that you see the vertical asymptote is close to 2, somewhere around 2. So you go to second table, get your points, around your vertical asymptote. See? If you get the error, that's for sure your asymptote, right? Because that's the restriction on your domain. That's exactly what you will not have. And then just take that and use the values. Right, so you can use these values and choose the points on both sides of your on your vertical asymptote, which you can get from this error here, which is the domain. Questions about this? Good. Okay, so we already talked about these tips. Whenever you use calculator to graph, just don't forget those parentheses. Otherwise, of course, the fraction will be different. And then this note about the asymptote on your graph that I already talked about. Questions?
Cool.